Hey everybody, welcome to another CS302 assignment. For assignment 4, we're going to be working with binary trees, but I guess the theme is going to be the flash. So essentially for this assignment, we're going to try to find the longest possible zigzag path, or essentially a path that alternates from left to right, right to left, the longest possible path. So it'll involve binary trees and doing pre and post order type processing. So for the input, you will process the input and construct a tree in a pre-order fashion, and then you're going to determine this longest possible alternating slash zigzag path in a post order type process. I guess the theme is the flash. The more zigzag he does, the faster he travels, which I guess, it does build momentum, right? So it makes sense. It's absolutely fits the theme perfectly. So let's go ahead and now discuss the contents of our binary tree class. So I forgot to put the heading right here that is going to be our binary tree class content, but I guess it is rather self-explanatory. So here's the contents of our header file right here. We of course have our header guards. We have a few libraries that we're going to be using in our header file. And let's look at our BinTree class. But within our BinTree class, we have our BinTreeNode class. Now, this could have been a struct instead of a class, but I suppose after CS2 or CS202, I guess classes are, they're a bit more fancier than a struct. I guess. I mean, I don't know, it seems like they're fancier. So when a class is used, it has more fanciness over a struct. I don't know, at least that's a preference. But anyway, so we're going to have this class, which will be really just a struct essentially, because everything in this class, BinTreeNode, is going to be public. And this class is defined within our binary tree class, which makes sense because really binary tree node doesn't really exist without really a binary tree class in a sense. So it does make sense to define this within our binary tree class. So anyway, in our BinTreeNode class, we have our char data, which is going to contain every element, every node's data will be a character type. And then we have our 2 pointers to our left and right child nodes. Pretty standard for a binary tree node. Then we have our two constructors right here. We have our default constructor, which will set our data field to an empty character. And we're going to initialize our left and right pointers to be null pointer. The purpose of this constructor is just so that way we don't have any undefined behavior. So we will ensure that when we do allocate a BinTree node, the left and right pointers will automatically be set to null. You of course can overwrite them since left and right are both public. This is just to ensure that when we do define our BinTree node object, it will be guaranteed that the left and right pointers will be set to null pointer. And our other constructor for a BinTree node class, this is going to just be passing a character type, or character parameter, sorry, and we're going to initialize our data field with that character, and of course set our left and right pointers to be null. So anyway, very simple class. So essentially you're going to have to maintain a set of binary tree nodes. We have to link them up together to create essentially a binary tree. Let's go ahead now and discuss the contents of our binary tree class. Okay, so let's go ahead and look at the rest of the private members of our binary tree class. I will sort of bounce back and forth between our private and public members. So we have our build tree function as a private function. This is going to be called within our public build tree function. So this public function is like a wrapper that's going to get called in main, but internally we'll call the recursive function. And I'll go into some of the details on that in a bit. Then we have our zigzag function. This function returns an integer, which returns the maximum zigzag found along the path. And we have a few parameters here as well, which I will address those more in detail later. We have the zigzag function here as a public member, which is basically just a wrapper. It gets called in main, but internally it's going to call this recursive function right here. And then we have essentially our pre and post order functions. Those are given to you. Now, basically, those are just to test out our we're going to test out to make sure if our binary tree was constructed correctly. So I have some additional mains I'm going to link to, or additional main, sorry, link to your BinTree CDP file, and it will just call preorder, which is given to you, which is the standard preorder post order function in CS302 class. But the purpose of this is just to ensure and test out to make sure that your tree is correctly being constructed. So I guess a little small test, and also gives you some gives you that validity that your tree is correctly constructed. So then you're ready to start doing the ZigZag content. The deallocate function is a recursive function. It's called in our destructor, which is going to essentially deallocate your binary tree. And it's going to essentially deallocate in post-order fashion. So the rule is you always deallocate your left subtree, then your right subtree, and deallocate the root of the tree. That's the idea. So just like post-order, except you don't see out, maybe you delete R. I guess I kind of gave away the deallocate tree, but that's okay. And after that, we have our BinTreeNode star root. So our private member will be root. So it's going to be the head pointer or the root of our binary tree. And our public member functions are all defined, given to us, except for this ZigZag function. You have to write this, but the constructor is given here in the header file. Sets root to null. Our destructor, just calls deallocate tree. Our build tree function, a public one, is also given to you. This is going to be build tree. You pass in a string. It's going to contain the entire input from the file. And then you're going to then call the private recursive build tree function, pass in the input, pass in the index of where you're going to begin traversing your string. And of course, it returns a pointer which root will catch the entire binary tree. Then of course, these public pre and post order functions, you call these in main. And this is also a wrapper function. So main, the test main I give you, it calls this preorder, and then this preorder calls the overloaded recursive preorder functions right there. I also have these definitions or these explanations right here as well in the PDF, but of course, I will now go into some more detail. I'll go into the details for the build tree function and of course for the ZigZag function contents. Let's go ahead and get started. Okay, so on the screen here, the left side, this will be the input file that's supplied to you. And ideally, you want to create this tree from this input file. So again, you're going to read this into a string. Now, I give you the main file right here, which essentially reads in the entire input from the file, and it sort of concatenates every character one by one into this input string. So the result is going to be your input string looks like this. So you have to essentially traverse this string or this character array in pre-order fashion. So the way it's going to work is right here for A at index 0, A's left child will be index, actually I won't put the brackets here because it's too much work for me. So that's index 0, its left child will be index 1, and the right child will be at index 2. Now if you look at B, you will see here for B is index 1, its left child would be right here, which would be 0, 1, 2. So it's going to be at index 3, and its right child will be index 4. So you have to essentially compute the left and right child index and assign B's left child to be D and B's right child to be E. And of course, as you traverse this, for C, C's index 2, so its left child, so 2, 3, 4, 5 right here, would be null. So the dash implies a null child. Index 6 would be C's right child. So I give you these formulas in the PDF so that you can calculate the index of where the left and right child in this potential array would be. So let's go ahead and sort of go over how do we actually construct this. But I hope this idea just kind of helps you out. But you want to traverse this in a pre-order fashion. So in other words, you start from A, then you go to B, then you go to D, and then you go to these two, I believe, right here. So that's going to be the idea. So you want to traverse this array in this kind of weird recursive fashion. Let's go ahead and just go over the how you would code this. So in the build tree function, the public build tree function, I gave you the code where you just simply just say root equals build tree, pass in the input string and pass in the starting index. So the root node would be index 0. So within the function body build tree, what you want to do is possibly just define a pointer. So this is going to be in the overloaded private build tree function. You're going to maybe create a pointer. Let's call it R for now, but call any variable name you like. And then you can say R equals new BinTreeNode. I would pass in input, and I believe the formal parameter in the build tree function will be input, and I believe the other one is index. So in this context, oh, too far to the right, so I couldn't fit this here. Anyway, for this context, index would be 0 in this context. So what's going to happen is you essentially have your R pointer right here. We allocate a node. R points to this new node, and we assign essentially, oh wait, oops, I made a mistake, sorry. I meant to say it's actually input bracket index, my mistake. So what's going to happen is we call the BinTreeNode constructor, and we pass an input at index. In this context, index would be 0, so it would grab the letter A and put that into the data field. And our constructor is going to set the left and right child to be null automatically, which is good. We want it to be by default set to null. So after this, what we want to do now is, well, we want to essentially recursively construct the left side. So you have to call the function build tree, pass in the input, and maybe pass in the left child index into this function. And what it will do is my call recursive function returns back an entire tree to me. But I believe the root of this tree is going to be B. And then we want to catch it right here. Then we have to call the recursive function build tree again. And then that recursive function build tree returns the address of the root node of the other tree, and I want to essentially have R arrow right catch it. And the root of this tree is going to be C. So we can see it's going to be a little bit of a pre-order process. So we create our node R, allocate the node, assign the data field to it. Then we have to call 2 recursive functions. Each are going to return back to us 2 subtrees. You want to catch it on the left and right side. And we have to make sure we pass in the index of A's left child, and of course the next function called we pass in the index of A's right child, and it sort of by magic constructs these 2 trees, and then R left and R right will catch it. Then at the end we have to return the address of R, because of course after we build these 2 trees we have to return R, and the root node, when we call the function build tree, the original build tree, the public build tree function, this function returns the address of node R so the root can catch the node R, which can catch A, and that's the idea. So it's going to be, I mean, I know this might have been a little bit too much magic spell going on here, but I can't give away too much. But in a sense, if you listen to my words closely and listen to the magic spell, it's actually, I gave away the solution essentially right there. So of course you can go back in the video and re-listen. That's going to be our build tree function. Let's go ahead and now discuss some implementation details of the ZigZag function next. So here's your BinTree SCP file. You have to implement these 4 functions. It's not that much work, and each function is not going to be huge really, so it's definitely doable within our time frame. So you'll notice in your main file, you're going to call the ZigZag function. So you have to, of course, write the code for this ZigZag function. This one's going to really just essentially process the root node, or it'll work on the root. And then you have to recursively call this ZigZag function on the root's left and right side. This recursive function does essentially the same exact work. So this first ZigZag function just initiates the recursion. This is going to call this ZigZag, which this ZigZag function is going to recursively traverse the tree. So at the very beginning, you call this ZigZag function, this top one right here. So it's going to essentially, your R pointer will be the root node. Actually, we'll look at root for right now. So you want to, of course, call this function ZigZag recursively on root's left and then on root's right. So what's going to happen is in this function, in this recursive function, you're passing in R, and you have its bool direction. And the purpose of this is to tell us, so for example, right here, when R points to B, R was the left child of its parent. Just like right here, for example, this R is the right child of its parent. And this R right here is the left child of its parent, correct? So the Boolean is there to tell us, because when we're on node R, so when we're right here at this node, or even like let's say at this node, how do we know what direction we are? And the answer is we don't know. We know we're someone's child. We have no idea if we're a left or right. So passing in a Boolean, true and false, will tell the node R if it's a left or right child. So if the direction is true, then we can sort of interpret that as R being a left child. If direction contains the Boolean false, we can interpret that R is a right child. So right here, we would be passing in true into this function and false into this one. So that way these two R's can tell whether they're a left or right child. And the path length is going to be your current path length. So right now, the path length of each are going to be 1. Because I guess for right now, if we start from the root, if you go to the left, then there's, I guess there'll always be at least minimal 1 zigzag path, if you will, because you moved from the root to the left. So I guess we can treat that as a left turn, right? So that'll be left, and we go to the right, it's also 1. But then from right here, looking at B, how do we know if we hit a zigzag? Well, we know that we have a right child. So we have to know that we are in fact a left child, and we can check we do have a right child right there. So obviously, we can add to our path length and pass in a different path length amount into the function where R would equal E. But if we go to the left, when we go to the left, of course, well, then we don't really tack on because we're still going in the left direction. So we didn't really zigzag. So if we go leftward, however, that means we know, oh, okay, that means we actually, we're not going to add on to our path length. We're going to reset the path length back to 1 because going to the left is not going to continue that zigzag chain. It's going to essentially start over again, if that makes any sense. Same idea here. When R points this node C, well, there is a left child over here. So on the left side of C is a null, so we can continue to zigzag, but we of course can go to the right, and we have to restart. But from F, there is a left child right there, so we can add on to our zigzag. So when we hit a null, we return the path length up, and of course the parent will then compare, because right here, after we do all this recursive work, the magic will be like this. At the root position, when we call zigzag, what should happen is this returns back to us 2, and this side returns back to us 4. So the bigger of the two is 4, we return a 4 back to main. And of course, for this first input file, the output is 4. But the idea is we have to, of course, return the path lengths up and, of course, compare at the parent level. But the parent initiates the recursive function by determining if the left child is he going to add to our zigzag or is he going to restart our zigzag. It's a little bit of both pre and post order, if you will. So the function is not very large, but it's a little bit tricky because recursion involves magic. But all you have to do is when you're on a node, just determine, are you a left or right child? And determine if you go to the left, does that add to our zigzag? Or if it doesn't, then we have to restart back to 1. But if it does add to our zigzag, we want to pass in path length plus 1 into a new function call. So we're constantly adding 1. So again, I might have given, again, a little too much help, but I really, it's really hard to be able to visualize the magic at times. I'm hoping that this gives you some insight. I don't want you to have to really stress too much over this assignment. But anyway, this gives you a chance to sort of think recursively and be able to do more of that magic in pre and post order and so forth. Okay, let's go ahead now, just go over the execution of this program, and then we can end the video. Okay, so to compile your program, as always, you would just do G++, and we have our BinTree.cpp, and then we have main.cpp, which will compile your program. There we are. To run this, we do /a.out, and we're going to use the Linux redirection to read in the inputs. So I think I called it flash01.txt, and then there's the output. And of course, we can do the same thing for a flash, other input file, and so forth. So you will only submit just BinTree.cpp. This main file will be already given to you on CodeGrade, and the header file is also going to be available on CodeGrade as well. And again, I also provide you with a test main. So let me go ahead and show it over here. So vim test, test tree, I call it, sorry. So there's our, again, it's actually very basic. All I do is I do the same exact thing. I just essentially do the same code. I construct our tree, and I simply just call pre-order and pre and post order right here. This is just mostly to help you test out to make sure that the tree was in fact correctly built. So it's a kind of a nice way to check for that. And of course, on CodeGrade it also checks this as well. So in our fancy Vim editor, let's get out of Vim for a second. And of course, to compile this, G++ BinTree.cpp and testtree.cpp. Same idea, a.out, flash01.txt, and it outputs your tree in pre and post order fashion to help you just to verify it correctly was constructed, to give you that assurance that everything is kind of working, at least the tree was constructed correctly. So at least, again, the worst case would be trying to check your zigzag function, but then all along your input or your build tree was actually wrong. So your tree wasn't even correctly constructed. So zigzag has no chance of working. So it's a way of being able to just try to isolate any possible bug. So that way, if this is coming out correct, okay, then at least you have that down. So now, then if there's something wrong, then it's got to be the zigzag function for some reason. So anyway, that's going to be the end of this video. So hopefully this video gave you some help on the assignment. So I guess happy coding, and till next time.